PowerWorld, this training isn't to go through a lot of the theory on transient stability, because I know you've had a course on that, and we're going to focus more on the practical aspects of how to use PowerWorld to solve transient stability problems. So it's very hands-on. The first one here isn't that hands-on, but after this first one, it gets very hands-on. The people that are going to be talking today and tomorrow and Thursday are Caroline, whom a lot of you know, who's been with PowerWorld for 10-ish years, right?
There you go.
Yeah, 10-ish years. She's actually one of my students. She was a master's student of mine. Then went off and worked out in industry and came back and worked in PowerWorld kind of on the software side. Jamie Weber is the key developer at PowerWorld. Jamie's been very involved with transient stability and has been working both on the technical side of how we model the grid and also on how we do plots and stuff like that, sort of the human-machine interface. Gordon, you all know, Gordon's going to help particularly on Thursday as we get into the actual studies, right? And then myself, I'm a professor at University of Illinois. I actually have to get my final grades in for my green electric energy class like today. So it's like I finished grading the exams, but I have to get them recorded so the students find out what they get. But I'm also a co-founder of PowerWorld Corporation and have been involved with the PowerWorld software actually since I started writing it in 1987, although it wasn't known as PowerWorld at the time. And then have gotten involved in the transient stability. I was the one that sort of pushed PowerWorld saying, hey, we really need to do transient stability. So I did practically all the initial transient stability coding and have continued to be quite involved in the transient stability software development. So we started doing this in 2006. PowerWorld as a company has been around since Mark Laufenberg and I started it in 1996. The first edition actually came out in, I call it my book, but I really came on as a third author in the fourth edition of that book. But we put transient stability in the book in I think it was the third or fourth edition of the book. That transient stability got into PowerWorld with version 12.5. We're coming out with version 19 sometime this year. So currently we're on 18 and we're working on 19. The reason why we did this is we saw transient stability was becoming important, not just in the West where it's always been important, but also in the East and in ERCOT as well. It was a natural fit for PowerWorld because we think of our expertise as one, really good customer service, and then we're good at dealing with large amounts of data and power system visualization and information management. And when you have the power flow, you're doing a snapshot. Transient stability is sort of a whole bunch of snapshots. So you change the dimensionality of your data. You take the power flow data, then you add another dimension because you're looking at snapshots over time. So that fits really well with how we manage data. And I think you'll see during the course of the training that we're pretty good at managing the data, and we'll explain how to do that. We're going to talk briefly today about very quickly on timescales for power systems, and then we'll go through some of the models, which we'll talk about later on throughout the course, and talk about how you see parameters for these models.
So Tom, could you go over the user base of the transient stability now? Since this is kind of the new kid on the block, 2006, and who in WEC, because most WEC users are using PSLF, and then there's some that are PSSE, and then also you've got the international clients that are using it.
I think a lot of people are using it. Certainly you guys, a lot in the Pacific Northwest. Seems like we're getting more and more sales on transient stability, but I can't give you a particular number on it. I will say that associated with my work at University of Illinois, we've been doing a project actually through Terry with BPA on doing transient stability software validation, and a lot of that project was validating the transient stability packages from GE, the PSLF versus PowerWorld. So we've been doing that for 3 or 4 years. And they match quite closely. TSAT doesn't match as closely with either of them. So we're doing that project. But people naturally have a concern, are you guys matching PSLF out in the West? And I think the answer is yes, we match PSLF really well. And I've done a lot of studies looking at why we match or why don't we match. Okay. And this is looking at time analysis of a power system. Some questions engineers might be asking is, what happens when lightning strikes a line, black start on transmission line, changing the output of a coal plant, loss of a large generator, and the key transient stability fault we run is the double Palo Verde fault in the West, and I've run that a lot of times. What happens when you switch on the lights? All these are time domain questions, and it requires time domain simulation, but it requires simulation on different time scales. And I just want to briefly go through some of the different time scales so you understand where transient stability fits in, what it's used for, and what it's not used for. If you want to look at the impact of a lightning hit on a transmission line, what we'd call lightning current pulse, the lightning strikes have a time scale that by the time you get to 20 microseconds, the lightning's gone, or at least it's rapidly decaying. The frequencies on that then are quite high, many kilohertz. If you look at a switching surge, such as when you put a line in, you're going to get a surge propagating down that line at nearly the speed of light. That's going to be very fast, and you have to take into account the propagation delays in the network. Take so many microseconds for it to get from one end of the line to the other end of the line. Then you get reflections, you get a doubling. That's a very fast phenomena. Here's an example of something that's called stator current transients. When you're modeling an electric generator, as you go through the development of the models, you start out and you get something that's known as the stator transient, which are very fast oscillations on the stator of the machine that can be in the 100 to 200 hertz. So this is slower than lightning, but it's still faster than the underlying 60 hertz signals. So those are something that is out there, but it's not something that's considered by transient stability. There's something called subsynchronous resonance, which can be an issue when you're doing wind turbine, wind farm modeling. It also occurs in other aspects of the grid. These are oscillations that occur on the order of maybe 15 to 30 hertz in the system. Subsynchronous resonance is something that actually transient stability does not address either because of the model time frames. If you want to model something faster than 100 hertz, or even getting into the 30 or 60 hertz range, what happens is you have to consider the fact that when something occurs in one end of the WECC, it does not propagate instantaneously to the other end of WECC. So if you think, how fast does light go? Yeah, 300,000 kilometers per second. So it goes, or since we're in America, we can say miles, 186,000 miles per second. It goes 186 miles in a millisecond. So when we do transient stability studies, we're going to use a time step of about 4 milliseconds. So in 4 milliseconds, light can only go 700 miles. So it cannot cross WECC in one time step. But we're going to, in doing our modeling, we're going to assume that it does. So there's a bit of a trade-off in the modeling here. When you solve the power flow, you're solving a set of algebraic equations that you're saying, across my grid, I have this power balance that occurs everywhere. That's not taking into account transmission system delays because of speed of light effects, because in a power flow, they don't come into play. When you start getting down into the shorter time scale, you have to do that, and that's what something called the Electromagnetic Transient Program, or EMTP, does, which BPA played a big role in the development of that software. That's not what we're talking about today. What we're going to talk about today is transient stability, which sits in the time scale from maybe a cycle up to seconds to perhaps minutes. And the models are set up for that. When we develop the models, we're going to ignore things like stator transients because they're too fast. So what do? Well, if your real system has these high-frequency oscillations on it, you might just say, I'm going to take this and assume that the dynamics are so fast that I can replace them with an algebraic constraint. So if I've got signal 1 here, I might just say signal 2 is 0.06 of signal 1. So I've replaced dynamics here. I say, hey, they're so fast and they don't matter that much by an algebraic constraint. And that goes on in engineering modeling all the time. We can't model the universe. We have to make to model the universe in full, you would need the universe. So we need to make approximations, and that's what engineering is all about. This is a time scale of the power system phenomena that we borrowed from a book by two of my colleagues, Pete Sauer and M.A. Pai at University of Illinois, Power System Dynamics and Stability. Just kind of puts things in the time scale. Here's 1 second right there, a tenth of a second, a thousandth of a second, and faster. We go very fast, lightning, switching surges, then we get stator transient, subsynchronous resonance. Then we get into transient stability time frame, and that's what we're going to be talking about today. We're going to talk a lot about machine dynamics, something about load dynamics, governor dynamics, but transient stability does not tend to get into longer-term issues, like usually there is not a model for the area control error response on a system. Now, we have recently added that to PowerWorld Simulator, but it hasn't been in there. Hopefully it'll get in there more in the future. But then as you get into longer-term response, like boiler dynamics that can go out milliseconds, those tend to be ignored in transient stability. Power flow kind of fits in this time scale where you think of it as quasi-steady state. The load is changing, but in the power flow you assume it's constant. There's dynamics on the generator, but in the power flow you assume that you just have a PV bus. Power flow is used to determine the quasi-steady state operating point, so we're solving a set of algebraic equations where we just say, hey, the power balance at every bus is equal to 0. We do the real power and reactive power balance. That's pretty straightforward to do, and that's what we teach in undergraduate power system analysis classes. But then when you develop commercial power system analysis tools like PowerWorld, you have to get into the details of how do you model these LTC transformers, what equilibrium point are they going to get to. Generators are PV buses, but there's a lot more to it because you've got to deal with how do the switch shunts play in, how do the phase shifters play in. We've put a lot of enhancements into PowerWorld to deal with this, some of them funded by you guys. Okay, so power flow is pretty involved, but it's looking for an equilibrium point. So the idea on power flow is if you take a power system that's operating in steady state and you put a disturbance on, like it could just be opening a transmission line, the real grid is going to oscillate some, and then it'll settle down to a new steady state value. When you run power flow contingency analysis, it's telling you that new steady state value. The assumption in power flow is that the dynamics settle down. Okay, but maybe they don't really settle down. And then you get into something where power flow might say you're okay, but you can't go from that point to that point. That's where transient stability comes in. Transient stability is primarily used, it looks at things like what happens during a fault on the system, what happens when a generator opens up and the frequency is no longer at a uniform frequency, and that's what we'll be covering in this course. Okay, so what we do in transient stability is we actually are still solving a set of equations that are close to the power flow equations. We call them the network power balance equations. They enforce the algebraic constraint that says, hey, at every node in the system, the P coming in has to balance out. We treat the whole system as coupled set of algebraic constraints. So the fact that if you open a line here in Vancouver, it's not going to be seen in Alberta, it's not going to be seen in New Mexico until so many milliseconds later because of speed of light propagation. That we ignore, and that's everybody ignores that when they do transient stability. But then we had a set of differential equations that model the dynamics on the system. If you've taken an undergrad power system analysis class, you understand about the swing equation. You see how the rotor angle changes with time. Those are some of the differential equations that we model. The model reflects the transient stability time frame, and in doing this, there's embedded assumptions on it, and you do have to understand, at least to some extent, the embedded assumptions. PowerWorld uses the same embedded assumptions that other packages like PSLF use. So the ultra-fast states, like the stator transients on the machine, you may or may not have heard of that. You may have done a lot of transient stability runs and never heard about stator transients. That's because they're treated as algebraic relationships. I had one of my engineers who works in the EMTP arena using something called RTDS. He was comparing it between RTDS, which is a fast simulation, and PowerWorld, and he thought if he just put a small enough time step into PowerWorld transient stability, he would see the stator transients. He didn't see them because they're ignored. And then, if things are slow enough, they're held constant. So usually in a transient stability run, we don't have dynamics in for the taps on the generators, the LTCs, that can be such a pain to deal with in the power flow. They tend to be held constant during a transient stability run. You can include dynamics, and we've coded up dynamic models, but usually they're not included. So how does a commercial package like PowerWorld work in a transient stability solution? What we do is you need to start out with a power flow solution. If you don't have a power flow solution, you can't solve transient stability. So when you start running transient stability in PowerWorld, the first thing it does is solve a power flow. That gives it its initial conditions, and then what we do is we back solve those initial conditions to figure out what's called the state variables. This is something that in an undergrad power system analysis class you use to get the internal angle on your generator. We do that. We back solve through all the models, through what we'll go through the machine models, the exciters, the stabilizers, the governors, and set all the initial values of the state, what we call the state variables, so they're all set equal to steady state. When you start a transient stability and you don't put a disturbance on it, should run flat. Nothing should change. If you've used transient stability commercial packages, you know that a lot of times that's not the case. Okay, and the reason why that cannot be the case is when we set these state variables, sometimes the power flow solution has pushed the state variables to limit violations. And then what do you do as a software coder if when you back solve, and let's say I get a field voltage, and the field voltage is 2.5, and you've got a limit in there that says, no, it can't be higher than 2. What are we supposed to do? Okay, these are what we decide as designers. And there's different ways you can deal with it, and we'll go through that later on in the course. So assuming we have a flat solution, or even if we don't, it doesn't matter. You're just going to see initial oscillations if you don't. Then you numerically integrate these differential equations. And there's different ways to numerically integrate differential equations. The simplest is a forward Euler method. It's simple to explain. But we use in PowerWorld a little bit more advanced method, which has better numerical stability.
Most of the power flow software marks the sequence, so they assume the power system is bound. So initial conditions come from those. How does it work where the system is tuned down and stuff like that?
the question was, power flow packages use positive sequence. How do you deal with imbalance when the system isn't really in a balanced, it can't be modeled as a balanced three-phase system?
How significant is that impact to the initial conditions, the use of the initial conditions?
And how significant is the impact of the unbalance on the system? Power flow packages, most packages are positive sequence, so you're assuming a balanced three-phase representation. It gets unbalanced when you put a fault on the system. So I think the PS in PSLF is positive sequence load flow. PowerWorld uses a positive sequence model, and that's true in transient stability as well. The way we model unbalanced conditions is just from a fault condition, and when you put a fault on the system, like a single line to ground fault, you use a compensation technique where you kind of treat that fault as if it were just in the positive sequence value, but the current takes into account the negative and the zero sequence from the fault. But to do that, you need to have, if you want to do that, you need to have a negative sequence model and a zero sequence model for your system, and a lot of times those aren't in the data sets. But PowerWorld can handle, because we do fault analysis, we can handle negative sequence and zero sequence models and then use them in transient stability. But we're not solving transient stability on the negative sequence or the zero sequence. What we start out with is you start out and you get your initial conditions, you set some initial time, and usually time is set to be equal to 0. You have to choose a step size, which is going to say how fast are you integrating your differential equations. By edict, WECC uses a quarter cycle time step. Okay. The time step could be shorter than a quarter cycle. It could be longer than a quarter cycle. The problem is if you set it much longer than a quarter cycle, you can run into numerical instability issues where your system itself is stable, but it looks like it's unstable because the integration method is not numerically stable. You can run it shorter than a quarter cycle, but it just takes longer to solve them. Okay, so usually the cases that you get have been tuned by somebody for a quarter cycle. And then every time step we go through and we solve the new value of the state variables. We use those to solve the new set of algebraic equations, the network boundary equations. Then we increment time and we repeat until you get to the end of a study. So you might do a 30-second study. If you're doing a quarter cycle is 240 time steps per second. So that means to do 30 seconds, we're doing 240 by 30, which is 7,200 time steps. And each one of those time steps, you could get data to display, so that would give you a lot of data potentially to display. There's tricks in dealing with integration. We'll get into block diagrams a little bit later on. If you aren't familiar with block diagrams, I was very unfamiliar with block diagrams until I started doing transient stability development in 2006. Since then, I've gotten quite familiar with block diagrams. But when you do block diagrams, this might be on an exciter or a stabilizer. You get a signal coming in. It goes through, in this case, it'd be a lead-lag block. The details here don't matter. The point is, a lot of times those have limits on them. How the limits are enforced is important. And there's something where if something violates its limit, you can either cap the output of that block at the limit and let internally the limit wind up, or you can just cap the output and then not let your states wind up. May seem like a very subtle distinction, but it can have a very strong difference in your response. Because if a limit winds up and it gets to go internally past its limit, once the input goes low again and it starts to come off that limit, if it's got a wind-up limit, it could take a long time to come off of that limit. We recently ran into this with testing of PowerWorld versus PSSE versus PSLF on how hydro governors' limits were enforced. And it turned out that in some packages they were allowed to wind up, and that had a tremendous difference on the output. So WECC addressed that, and it's been taken care of. But it had a major impact on the output. Something that's a little subtle is a lot of times when we study systems, particularly with exciters in them, sometimes with stabilizers, that quarter cycle time step is too large for the dynamics that are going on in the exciter or stabilizer, or sometimes it's within induction machines. So we have to do what's called sub-interval integration. So we actually take the integration for these models and make it even more fine than a quarter cycle. So this is what we call sub-interval integration. As a user, you don't have to worry too much about this unless the model goes numerically unstable. So PSLF does this as well. You're just trying to allow faster dynamics to be modeled, and it occurs internally in the system, but you should be aware of it, and we'll get to that when we get to the models.
For that scenario, you internally modify or change the time step as the transient goes on?
The question was, do we internally change the time step? We do, but just for that model. Like when we do a WECC run, we might be running 100,000 differential equations. On, let's say, one exciter that has 5 differential equations, we realize that we need to use 1/64th of the quarter cycle time step. So we will internally modify the time step, but just for that single exciter. So then we run 1/64th times 1/240, so you're doing a very small time step. If we did that for the whole system, it would take forever to solve. So we just do particular models.
If you're going to cover it later, that's fine. But when should we guess that maybe it was a numerical instability as opposed to an actual system instability?
Okay, the question was, when should you guess whether it's numerical versus an actual system instability? We'll cover that later on to some extent, but there's no cut and dry. I mean, you can't tell for sure because they show the same results. There is one trick would be if you do a run and you have the time step and you get the same response, then it was probably an actual instability and not a numerical instability. If you have the time step, which you can easily do in PowerWorld, so rather than a quarter cycle, you run 1/8 of a cycle, it'll take probably twice as long, but if that instability goes away, then it's numerical.
That's one more question. You mentioned you had somewhat improved integration method your PowerWorld is using.
Compared to Euler's, yes.
Is the range in which numerical instability can be avoided, is it the same as typical range, or it's somewhat wider?
Well, if you run Euler's is much worse than what we use as Runge-Kutta. Runge-Kutta has a better region of numerical stability than Euler's does. So yeah, that helps out. I mean, we're evaluating the equations twice per time step, whereas if it was Euler's, you would just be doing it once per time step. When we get into modeling the physical components, such as a generator here, you would go from the supply side where you got fuel coming into your generator. Ultimately, you're getting a voltage and current out of the generator that is going into the network. This is algebraic here. You might have differential equations on your load. You definitely have differential equations in here. So these are the various components in the system focusing on a generator. The way these components are broken down is we use 4 principal models for an electric machine or electric generator. We call it a machine model, which models the dynamics of sort of the physical spinning machine itself. Then we've got a model called the exciter, which models the voltage control system. Then we've got a model called the governor, which models the response to the turbine and the steam valves and to some extent the furnace and the boiler. And then a lot of generators, particularly in your neck of the woods, have a separate system called the stabilizer, which takes an input such as the voltage on the generator or the speed of the generator, and then takes that and modifies it and changes the voltage input to the exciter. So there tend to be 4 major components on a machine, and you will see this throughout as we do the system modeling. Then something that WECC is getting more and more into is modeling the protection system. So there could be line relays out there, there could be load relays out there, there could be relays associated with the generator. All this plays into getting more and more models. And then the loads themselves have models associated with them that are getting more and more complex. This guy, Prabhakundar, came and gave a talk to you. Nice textbook. I've got it, and we've used it quite a bit in the development of this. Usually it's not used as a classroom textbook, but it's a great reference book. Jamie developed these slides, and he really got into the modeling of the machine. I'm going to go through these pretty quick because you've already seen that. But this is a classical representation of a machine. That's the stator. There you've got the 3-phase windings on it. If it's a 2-pole machine, you got the rotor, and there's windings on the rotor. This is the field winding, and you also would tend to have damper windings in there. You don't have to worry about that if you just want to say, I just want to take a model that somebody's developed, like John Undrell's developed a lot of those models, which we use. You don't have to get into the details on this. But that's what the machine model is actually representing. The physics here, the exciter is a separate system that sits outside that controls the field current and field voltage in response to changes in the voltage with the desire of keeping the terminal voltage constant. Then you've got the full mechanical representation on the system. Details on the modeling of the generator. Most people are familiar with the swing equation because it's covered in an undergrad class. But the gist of it is that when you've got a spinning rotor and you're looking at it in kind of a steady state representation, as though we're strobing that rotor, which would really be spinning at 3,600 RPM or 1,800 RPM. When you strobe it at the synchronous frequency, you can think of the torque angle on that generator as being constant as long as the mechanical power into the generator matches the electrical power out of the generator. When those two get out of whack, then you get dynamics going on, and a primary way for them to get out of whack is as a result of a fault. One thing that's very important in considering power systems is we use per unit a lot, and most of the data that you get is in per unit. So power engineers are pretty familiar with this. There are tricks in looking at the data. Sometimes it's in per unit and sometimes it's in actual units, particularly when you get into values that respond to frequency. We'll talk about this a little bit later on. Frequency values like particularly there's one called damping, which is never clear whether it's in per unit or in actual units. We did some work for some utilities in China, and in China everything is on 100 MVA base, including the generator parameters. Here in North America, the generator parameters are per unit, but they're per unit on the MVA rating of the generator. Here's the generator swing equation. Basically, it says that when the mechanical power divided by speed, which gives you torque, minus the electrical torque, is different, you get an angular acceleration on the machine. How fast that machine accelerates depends on the inertia of the machine. The larger the inertia, the less it's going to accelerate. One of the issues that's a concern in the power grid is as we take away high inertia units like coal plants, we're going to be changing the net inertia of the grid, so we might get more involved disturbances on the grid. This is details on the modeling of the machines, which I think I can skip over quickly here. More details, direct axis, Q axis. You only really have to get into this a lot is when you're coding in these machine models, which we have done a lot of at PowerWorld. I will note that one of the confusing aspects in the power community is some authors think of the direct axis as going in this direction and the Q axis is going up that way. Other people put the Q axis that way. And the reason it matters is if you're coding a model from one textbook and they've got the Q axis this way, then you go to another textbook and it's going the other way, it flips the signs in the model. Neither one is right or wrong. It's just a convention, but it drives people like me nuts. I wish we had just kept one or the other, but we do have two in the community. This is derivation of the rotor equations. You probably don't want to get into the details on that. DQ transformation. In PowerWorld, we're going to show you in the next set of slides how you get access to the model parameters. And something we've worked hard to do is to make it easy to give you access to the model parameters. There's the coupling, which we'll talk about later on. Different machine models. Classical model is the one that you've heard of most recent, or that's the one that's talked about in undergrad class, but it's seldom used now in practice. Then you get into more detailed models. I mentioned the Gen Sal model, the Gen ROU model, and then one that's quite popular now in WECC is the Gen TPF or the Gen TPJ models. So I think they're becoming required in WCC. We get into the details here. This is as coders, how we code these models up as we look at block diagrams like this. And when I started doing this in 2006, this looked like a mess. And it depends if you're familiar with them or not. If you don't get into the gory details of transient stability, usually you don't have to worry about this. But if somebody gives you a model and you're trying to figure out how come my transient stability run is not working, and somebody, rather than putting a KF there, they, maybe they forgot about a decimal point and they changed the gain from 1 to 10, and that drives your model unstable, that can be a problem. And if you have no understanding of how a block diagram works, that can be a problem. But it's certainly a balancing act because it does take a lot of work to really understand what these are doing, something that we've developed over the last 8 years or so, because we have to code this up. And it's one thing as an instructor, as a professor, if you don't understand something, you can just wave your hands and the students aren't going to get too detailed on it. And then if somebody asks you a tough question, the easy thing you can say is, well, that's not going to be on the exam. I'd be happy to talk about that if you want. And then they'll say, no. Like, ignore that. Then you can get by it. So, but we have to get into the gory details because we're coding them up. We have to back solve them. I will say that when you get a transient stability run and it does not initialize flat, that can be sometimes because, hey, I solved for this VR value and it's greater than the maximum. Okay? What do you want me to do as a software coder? And we give you a couple options in PowerWorld, which we'll talk about. A simple option is to say, hey, if this is 11 and that limit is 10, just change that limit from 10 to 11. And it solves the problem, but the question is that legit? Maybe it is, maybe it isn't. So the details do matter in the response that you get. Governors are the system that is used to control the speed on the generator. The governor senses the speed, and it ultimately controls the speed. It's sort of like keeping the speed on your car constant. But the idea is to run your system so you're at a constant frequency. And it's an automatic system, and there's a lot of different governor models that we've coded in. Speed governors, they're taking a speed input and changing the output of some valve. Droop is something that is used to make sure that you can operate a number of different generators together when there's a frequency disturbance. If you don't have droop built into your governor settings, you can get governors that fight each other. Try to synchronize two generators together without droop. If each generator tries to go to the same frequency, it's called an isochronous governor, tries to go to a constant frequency, they will fight each other. So this is key to how we operate the grid, and we'll point that out as we get into the details on the models in the future ones. I will say that with droop, the power system following a disturbance does not return to the 60 hertz steady state initial operating point. And that's key. In the real system, the automatic generation control would return the system to 60 hertz, but that doesn't tend to be modeled in transient stability. There are some models that help that we'll talk about a little bit later on, but you won't see in a transient stability run following a large generator outage the system coming back to steady state. Stabilizers, we'll get into details on those later on. Wind turbines is an area of a lot of development. WCC has been taking a lead in coming up with standard models on that. Load models is getting more and more complex, and we started out with simple models for how the load responds. In the power flow, you tend to use a constant power model. In transient stability, when we started out doing it, we as the industry would use constant impedance or constant current models, where if the voltage goes down and it's constant impedance, the power falls with the square of the voltage. But over the last decade or so, partially driven by BPA in the West, more and more dynamic models have been added.
Governor power flow and AGC reactions. How do you model AGC reactions along with, do you care at all, or just the governor response would be good enough in transient study? Do you care about AGC movement?
Question was on the governor response and transient stability, and then later on the AGC control.
Right, the AGC can also play a role in there a little bit later.
Yeah, the question is, I guess you're getting at why don't we have AGC modeled in the transient stability?
Right.
And transient stability started out looking at how does the system respond to a fault. So how does it respond within seconds after a fault? And gradually has gotten into longer-term studies where you might say, okay, I have a generator go offline, like in the West, it's a double Palo Verde fault, and maybe I run out 30 seconds and my generation returns to a steady state value, but it's not 60 hertz. Okay? And that's as far as people want to go. Could you run it further out? The answer is yes. You could run it further out if you want to run it further out. AGC doesn't tend to be included because it takes minutes, between dozens of seconds out to minutes to respond. Should we as an industry support the models necessary to do AGC? Because when you get into AGC, you have to say, following this disturbance, for example, the double Palo Verde, how will the generators respond to get back to 60 hertz? So you have to model the ACE, and you have to know how are the cost characteristics on the generators going to come into play on this. That's something we as an industry haven't done. Could we do it? Yeah, we could. And PowerWorld does do it for some places.
Yeah, Tom, isn't there also an issue that if you run a transient simulation out too long, maybe way past 30 seconds, for example, that you're starting to accumulate a little too much numerical error, which can also create some issues? Or is that something I've heard in the past? see if that's been your folks' experience as well.
Well, I could talk a long time about that. We've got a new product called PowerWorld Dynamic Studio, which does interactive transient stability level simulations that go on for minutes and minutes and minutes. And I put in a WCC model in that, and at 99 seconds, I got all sorts of stuff screwing up. Because in the model, people will put in 99 as sort of a value saying, we're never going to get this far. Okay? So, yeah, I mean, it's just a model parameter that says trip this stuff after 99 seconds. And so there's parameters in models where somebody might just enter in 99 realizing, hey, we're not going to run out 99 seconds. Now I do, and it comes into play. Does numerical error accumulate? It sort of does, but you're going back, because you're solving the algebraic equations, you are coming back to kind of an equilibrium point, so it sort of doesn't. In running WCC studies, are there some models in there, at least have there been models in there where they have slow modes of instability? And the answer is yes. Like, I'll take a model and I'll run it out 200 seconds, and it goes unstable. And I have the time step, and I run it out 200 seconds, it still goes unstable. It's a real instability in the model itself. Nobody sees it because nobody runs out 200 seconds. So that's a modeling issue. Obviously, the power grid itself runs more than 200 seconds, but you can have subtle errors that exist in there because nobody's doing it. As we start running out further, which we're doing now, they become issues.
Besides that, 99 seconds, say, hard-coded limit, or what other things could be in a model where over a long period of time it would go unstable, whereas in a short period of time it wouldn't? But, besides just having bad data where something has a slowly growing oscillation that eventually impacts all of WAG, is the problem.
It is possible to set up models that are stable, and you can run them out. We have run models of parts of the WCC for very long periods of time, and they're fine. This is something that we can achieve. Okay, but there are some slow modes that we'll talk about this later on, you do eigenvalue analysis on a single machine infinite bus, you see positive eigenvalues, which if you remember, if you took a controls class, positive eigenvalues are growing with time. They exist.
It's not necessarily even a model error. It's just.
Well, I don't think they exist in the real grid, but they exist in the model. So I would call it a model error. There's not a lot, and we can address them because we'll see all the generators settling down, and then one goes like that. And you just look at that model and you kind of figure out what's going on with it. Like there were some models that had negative droop in them, which is not a good response.
So what do you do when you see the positive eigenvalue? You just click the sign or do something?
Getting around to tuning parameters is a challenge. We do give you sensitivity analysis tools that you can figure that out with somewhat. It's not a simple thing to do. PowerWorld tries to make transient stability as simple as possible, but it's not like a simple problem. It takes very intelligent engineers doing this stuff. It's not, for the average layperson to do. Talking about complexity, we used to have for a load just one load there. Maybe it had some voltage dependence in it. Maybe it had a 30% induction motor load. Now where WCC is going is to treat the load as it really, getting close to where it really is. What's sitting behind that innocent little load at, let's say, a 230 kV bus or a 115 kV bus is a transformer. There's maybe capacitors embedded in there. There's feeders in there. Those feeders have static load. They've got electronic load. Increasingly, in some parts, they've got PV load, for the photovoltaics. Got motors out there, motors of all sorts, including the very quick responding compressors on air conditioners. That's all trying to be modeled by WCC. So what was a simple 2, 3, 4, 5 parameter model load now has more than 100 parameters associated with it. Okay, and life's getting more complicated for us. So we're trying to address that in PowerWorld with better tools to help you deal with it. But when you've got 130 different parameters, that's, more parameters to deal with. Any questions before we go on to actually doing something?
So just to follow up on somebody's question, just a quick follow-up. So the small time constant of an exciter model, for example, does not prevent that model to be simulated out to very long.
Yeah, the question was, do the small time constants on an exciter model permit it to be simulated out very long?
Any other model for that?
Usually if a model like an exciter is numerically unstable, it's going to manifest itself very fast. So that doesn't affect long-term simulation. If that model is numerically unstable, like if PowerWorld and other packages like PSLF, we do auto-correction of weird, let's call them weird or unusual parameters that we think are going to cause numerical problems. We correct those. Like if I have a very simple time constant modeling a measurement delay, you've got the actual voltage and it takes me, let's say, 0.05 seconds to sense that voltage. So it's a first order lag model. It's very simple to integrate. If I let that time constant go to 0 but not quite 0, I would get a numerical instability. So what our software does is it says you can set that parameter to 0 and we will ignore it. You can set it to 4 times the time step, which would be, if it's a quarter cycle, it would be 0.1 over 60. But you can't put it between 1 over 60 and 0. If you do, we're going to auto-correct it one way or the other, because we know that would tend to cause a numerical instability. So we're trying to help you out. If you say, but I must have it at that value, we can deal with that, but we'd have to go to the subinterval integration. But I don't think you must have it that's in that forbidden range.
Well, I was thinking about the thing running transients really long and you have these slowly going modes. I mean, is part of the issue that we don't necessarily model all the damping that happens and all the losses that happen in real life, so that in real life you get damping of those slowly going modes because, I don't know, you modeled with the kind of loss you could have, some kind of rotor resistance that we're not modeling, that's a bad example, or windage losses or something, or what's that flashback on rotor teeth, or other kinds of losses that are just not in the model that in real life would dampen those slowly going oscillations that we don't have, so that if you run it for a long time, you just get it.
Well, I do want to say, when we run WCC for a long time, and we have, very few models have issues. And so it's not like they're all out there. There's actually very few. The 99 one was something, but that's clearly just a parameter that I just changed them from, I put them to like 9999 or something. It just pushed it further out. So whether those are real issues or not, I don't think they're real, what we're seeing. I think it's just a parameter tuning issue. But if you don't test those models out long term, and why would you if you're only running 30 seconds, it's just as we decide. If we decide as an industry we want to run longer term, I don't think there's a problem with it. We just have to look at some of the models. And this is what we do as an industry on shorter term models. You get a new case and maybe somebody's put a wrong parameter in there, it gets caught right away if after 10 seconds it goes unstable. If it takes 30 or 300 seconds to manifest, it won't get caught.
I'm just curious if there's any, besides, having 99 represent infinity when it's really not when you run a long time, if there's any other issues in models that the model actually works really well in a short time frame, but you go longer and it's a problem. Because I think what you're talking about is models that they don't even really work that well in a short time frame. It's just they haven't gotten bad enough to destroy the whole simulation.
Yeah, I don't have any specific examples, but I know in the project that we did for BPA with University of Illinois and Washington State, we did pass over, Jim Gronquist was our contact, and we passed to Jim some models that would go unstable after like 300 seconds. And this was just because we would see something strange. We'd create two-bus equivalents, which we're talking about later on, and then run those out longer just to see what happens. Really, I'd do the single machine independent bus, and I'd see a small positive eigenvalue, and I'd think, is that really there? So I'd run it out 300 seconds, and sure enough, it is there. But it's a minor issue.
It's probably important to use the latest cases if you're using wet cases, because the modeling validation work group had the mandate several years ago to correct all this data, and still there's thousands of errors, but it's much better today than it was, say, 5 years ago.
Yeah, and I should say, we work more in WCC than in the Eastern Interconnect, and so it seems like WCC gets picked on a little bit more, but I see WCC as the leader. It's just the Eastern Interconnect and ERCOT and probably every other system that has models has the same issues. I think you guys are leading and tracking them down and getting them fixed.